Okay, then we can start. So, basically, today we'll be dealing with the third week lectures. So, if you have gone through the lectures, it mainly deals with the first part is somewhat related to what we were doing in the previous week, that is in the week two, that is related to the atmospheric water. So in that we were dealing with different terminologies, basic terminologies that were so important in this when dealing with atmospheric water. So based on that, how we can find precipitation intensity using those terminologies and with the help of the theory that is theorem that we learned, that is Reynolds transport theorem. So that is what the first part of the lecture was, to find the rainfall intensity. It is more uh, connected to the week two lectures, and if we have a good understanding of the week two lectures, it will be very clear. And the second part was totally based on the precipitation, that is rainfall. Within precipitation, see if you have gone to the lectures, you know there are different types of precipitations, right? So anything that reaches Earth from the atmosphere, that is in liquid or in the solid or the gaseous form, these all are called precipitations, which is a we can say general term. So within that, there are different types of precipitation, and mainly this the third week lectures we're dealing with the rainfall, which is the liquid form of precipitation, and which is the main source of water resource in for in when we say globally. So uh, so before I start, so I should give a brief introduction about myself. So I'm Akhil and I'm a PhD scholar from IIT Delhi. So I'm currently in my fourth year of my PhD, and I'm working. My research area is groundwater modeling, and I did my BTech from IIT NIT Calicut in the year 2018. I was graduated, and I did my MTech from IIT Guwahati. I worked under the supervision of Professor Srija Pekat, who is the course instructor for this particular course, and currently, I am enrolled for in PhD from the year 2022 in IIT Delhi. So we can start with the first problem. The first problem is based on a model that is called the thunderstorm cell model that we had already seen the lecture. Like that is what is the purpose of that model. So basically, that model is used to find the rainfall intensity if we know the different parameters of the atmosphere. So we got familiarized with the different terminologies and different parameters that define the atmospheric conditions. So if we know those values, if we can calculate those values, so then we can find the intensity of the rainfall that comes to the Earth's surface, falls to the Earth's surface. So using this particular model that is called the thunderstorm cell model. So, if you remember correctly, in the previous lecture, I showed you through the questions that if we are able to measure the parameters like pressure, temperature, air density, everything in the ground surface. So, if we could measure that, and if we know some constants like the lapse rate of the atmosphere, such constants, if we are familiar with, then we can measure it to any elevations. So, if you want to know those, there are many assumptions. So keeping those assumptions, if the lapse rate everything remains constant, then we can find these parameters at any elevations. If a given elevation, you can find that. So it is only thing we have to measure these parameters at the ground surface, right? So similarly, if we have the parameters in the ground surface, we can make use of this thunderstorm cell model with the help of the RTT, that is a Reynolds transport theorem. That is basically a theorem that connects the conservation laws, which are defined in the Lagrangian frame of reference, to the Eulerian frame of reference or the control volume frame of reference, which we can extensively used in fluids when we are dealing with fluids, that is gaseous or liquid forms. Okay, so first question is related to the thunderstorm cell model, so I can read it out. In the thunderstorm cell model, the mathematical derivation of rainfall intensity. So I already explained you, we are basically using this particular model to find the rainfall intensity. So rainfall intensity is primarily based on RTT. We are applying this RTT to which governing equation? So there are different governing equations, right? So the purpose of RTT is to basically use what we say, use these governing equations to fluids. So there is a gap that these are defined in the Lagrangian or point frame of reference. We have to convert it to the Eulerian frame of reference. So that's why we will be using RTT. But the question here is, if you are using a thunderstorm cell model to find the rainfall intensity, which governing equation are we trying to are we are trying to convert to the Eulerian frame of control frame of reference using RTT? So the options are conservation of momentum for air current, continuity equations for water vapor, energy balance equation at the cloud top, hydrostatic pressure equations. So can anyone tell the answer? Yeah. So continuity equation for vapor pressure, right? So to this question, I will give a brief recap of the thunderstorm cell model. So basically, the thunderstorm cell model or TCM, I'm writing it in abbreviated form. So basically, what we are saying is if we have an area, for example, you can take it as Delhi NCR. So we have the state of Delhi. So in New Delhi, we need to find the intensity of rainfall. So we are not measuring the rainfall. We are given the atmospheric parameters. There is a weather station where we measure all the atmospheric parameter. We want to calculate the intensity of rainfall that is going to happen. So to do that, what we do is we see the area of the entire Delhi. So entire Delhi, we assume that the atmosphere about us is assumed to be a cylinder with diameter such large that it covers the entire Delhi, right? Or if the rainfall is occurring in some particular location, so within Delhi, if it is occurring in the South Delhi region, so there we consider a atmospheric column or an atmospheric cylinder of a particular diameter of our interest, right? So if you now we are considering region Delhi where we have the atmospheric parameters, everything we have calculated. Now we need to find the rainfall intensity, right? So there, so this is the cylinder that we consider. So basically that cylinder has a inflow region. This is near to the surface. So this is our ground surface base, that is ground level. So from the ground level, we have already measured all the atmospheric parameters, right? So we consider a column and the column is having a diameter d. So this diameter is based on the area of interest that we are trying to find out. So now we are trying to model it for the South Delhi. So the diameter will be covering the entire South Delhi, right? So once we define our area and define our diameter of the column, then we divide it into three zones. That is the inflow zone. It has an inflow zone that is near to the surface and outflow region, and between connecting these two we have the uplift region. So it has three region: inflow region, uplift region, and outflow region. So basically, what we know is we have the pressure, we know the pressure value at the surface, we know the velocity of wind value, if we know the density value, if we know the specific humidity value, and then we know the temperature value. All these values we know we have measured at the surface, right? And we also know what is the lapse rate, what is the lapse rate of temperature. So what is the gas constant, what is these gravity. So all these constants also we know. So using these particular values here, we can find these values at this particular elevation, that is at elevation this Z1. And also we can find at another elevation that we calling as the this particular elevation. So this width we are calling it as delta is at 2 and this is delta is 1, that is the inflow region width and outflow region width. So at this particular elevation also we can calculate all these values, right? Velocity, density, specific humidity and temperature. And also at this particular location we can calculate all these quantities if we know at any particular elevation, and given that we know all the lapse rates, all the constants are known to us. So this already we solved few questions in the last class, right? We were given with the parameters at one particular elevation when we were asked to find all these parameters at some other elevation. So that we can do here. So we know the inflow region, these parameters we know, and also for the outflow region we know. Then what basically happens, what the mechanism happens here is that as we already saw in the previous lectures, different forms of lifting, like how the precipitation happens. The first mechanism was the lifting of air mass, right? So different forms of lifting was there. In that, one of the important form was lifting by convective lifting, right? Convective lifting is due to getting the water mass get heated up by sunlight. So when and then it gets evaporated and the warm air rises up and it condenses and the rainfall happens. For such cases only, we are applying this TCM model. So that is one thing you have to remember. So the TCM model is applicable only for convective rainfall. A convective rainfall means the rainfall that is caused due to convective action. Right. So this is also called convection circulation. So this particular circulation, that is the air mass enters through the inflow region. So air mass basically enters through the inflow region from the bottom and it gets uplifted. So the air mass means the surface gets heated up and the warm air rises up in the uplift region and it goes out in the outflow region. This is basically the mechanism that happens, and this mechanism is purely due to the convective action, right? And once this condensation happens into the outflow region, then it will falls down as rainfall. And our intention is to find the rate at which this rainfall happens. So basically, here the cylinder that we considered, or the cylinder of diameter that d that we consider, is nothing but a control volume. So if we have a control volume, we can apply different laws, right? We can apply the RTU with the help of RTT. We can apply different laws. So one of the so as you already said, so we are going to apply the continuity equation for water vapor in this particular column, right? So if you remember correctly, so the RTT, we have derived it as dB by dt is equal to d by dt of, that is rate of change of uh, the extrinsic property is equal to d by dt of control volume, rate of change of extrinsic property across the control volume plus rate of change of, not rate of change, the net outflow of the extrinsic property across the control surface, beta rho V dot dA. So this is the RTT that we have already derived, and we have already applied this to the atmospheric column also. For that we were getting this. So for that our beta was QV. Beta is nothing but specific humidity, and also B was the mass of moisture or mass of water vapor. And we already know that dB by dt is not equal to 0 because here the mass is not getting created or destroyed, but it is changing phase. Due to the phase change, so there will be the change in mass won't be equal to 0, and that we are calling it as m dot v. So basically this m dot v we are defining it as mass flow rate of water leaving this cell. So this is something that we are interested with, right? We have the what we have the thunderstorm cell model. So how much, what is the mass of water leaving the cell? So that is something relate what we are interested in. That is something that can relate give us this particular rate, right? This particular rate of at which the rainfall happens. So this particular term, so with the definition of m dot, we'll be stopping the discussion of the thunderstorm model. So I just wanted to know how we are getting this intensity. So we know that the phase change is happening, and also in the previous class we saw the questions where this m dot v takes the signs of positive and negative. That is, if it takes the sign positive, when more and more water vapor is getting added to the system, that is when evaporation happens, right? And it is negative when more vapors are get converted or destroyed into liquid. So that is when condensation happens. So if the rainfall to happen, then the condensation should be predominant, right? So this m dot v in this CCM model will be negative. So this m dot v, that's why we are calling it as leaving the cell. It will be have a negative value, right? So that will be equal to mass flow rate. So mass will be equal to density of water into intensity into area. Right, so this, if you want, this is the equation for the mass leaving the cell. To make it clear, we can start with the definition of mass. So mass, we can write it as, or definition of density. Mass is nothing but density of water into volume, right? So, so this is what mass is. So mass flow rate will be density of water into volume divided by time, right? So this, if you write it as this volume, we can write as area into length, right? Base area into length is volume by time, right? So this particular term is nothing but intensity. That is the length by distance by time is nothing but the intensity. Intensity is nothing but the rainfall happening per time. So there we can write into area into I. So this is how we get this particular expression. And from this expression, if you could see, we have a term which we want to derive. That is I. I is nothing but intensity of rainfall. Intensity of rainfall. So in this case, if we have, if we could apply this RTT theorem, so our LHS is having the term which we are interested in. That is the intensity of the rainfall that will happen in the column, right? And the RHS, we can make some assumptions, like we make assumptions that it is a steady state, then the first term gets cancelled, and we are only left with the net outflow. In that we can apply the RTT for the outflow region where we have the dry air. So such derivation we have already seen. So such simplification, we'll be finally getting an expression for intensity. Right, so LHS, we have the intensity term. RHS, the first term we can cancel because we are taking the case of a steady state. So it won't be the, what we say, the extensive property won't change with time. And the second term is a net outflow. Net outflow means the inflow minus outflow. So inflow, we can derive an expression, and outflow, we can apply RTT for a dry air case. Then we can get a simplified expression for I. That is how we apply the RTT theorem to the conservation of water vapor mass and get the apply this for a cylindrical cell or cylindrical column, and we get the expression for intensity. This is one of the way to find the intensity of a rainfall if we know all the parameters in the ground surface, and provided we know these values of these constants, we can find out these values parameters at any elevation, and we can apply this, and we can come up with the expression for the intensity of the rainfall. So the expression I will be giving you in the numericals we have a problem, so there we can get familiarized with the expression. So as of now, this is the theory behind this. So as you said, it is as correctly the continuity equation for water vapor is what we are applying the RTT to get the in TCM model to derive the intensity. Okay, so next we can move on to the second question. So this is a simple question. It is a repeatedly asked question in like the previous, like in GATE and also some state PSC questions. That is, which of the following is not a form of liquid precipitation? So in the starting of the lecture, I already told you precipitation is a general term. So whatever that falls from the atmosphere through the clouds, on the clouds to the and reaches the earth's surface, we call it as precipitation. That is a general term. So you will be confused or you will be familiar with, we are using this term like rainfall and precipitation. Like somewhere we use precipitation, somewhere we use rainfall. See, so it's nothing but rainfall is the liquid form of precipitation. There are different forms, like solid forms are there, liquid forms are there, and very what we say, very light or very small, minute size of droplets will be there. So these are different forms of precipitations can be there. So based on the size of the water droplets, we can classify this into different forms of precipitation, right? So in this question, it is asked which are not a liquid form. So can you answer this? Mm, which is not a liquid precipitation. Yes. So rainfall, it is obvious, right? Rainfall is not a, it is a liquid form. So that is very much familiar, and there is no doubt in that. So rainfall, but the thing you have to remember, few things that you have to remember about rainfall is the sometime they may ask this question also, what is the size limit of the water drops that, so that we can call it as a rainfall. So that is if the water, so basically rainfall is are water drops. Is a liquid form of precipitation, and it is made of water drops. And the important thing is the size. So the size is between 0.5 mm to 6 mm. So every liquid form of water that is coming from the atmosphere to the earth is not, we cannot call it as rainfall. We can call it as rainfall only if it has a size between these two. Okay, so these are the limits. So that is the only thing that you have to remember. And the second option is called drizzle. So drizzle is also a familiar term. So when we have a very light rainfall, we call it as a drizzle has happened. Or in the news, if you see, they will be reporting it as a drizzle happened in Delhi or something. That in the news headlines you could be familiar with this. So this also, it is not a casual term. It is also has a predefined definition and the so technical definition for that. So it is water droplets only. It is a liquid form only. This is also a liquid form, but it is of very small tiny droplets. Small tiny droplets. And here also, when you are looking for the competitive exams and all, here also you have to be uh, familiarized with the size. That is, you know already the limit of rainfall, right? Rainfall is 0.5 to 6 mm. So if it is less than 0.5 mm, then it is called drizzle. So along with this, there is one more thing, that is the intensity with which this happens. So the rainfall has, one is the drop size, another thing is the intensity. So here the intensity will be less than 1 mm per hour. And in case of rainfall, the intensity is usually uh, can be based on intensity, we can classify it as from 0 to 2.5 mm per hour. This is as a light rainfall. This is classified as a light rainfall. And 2.5 mm per hour to 7.5 it is moderate rainfall. We can see how the value is like the very light rainfall also has an upper limit of 2.5 mm. Here, if you see the drizzle, it has only 1 mm. So these water droplets, when it happens, if we have the wind speed, so these will be carried away by the wind speed. When mostly it won't be reaching the earth, it will be floating in the atmosphere, right? So this is how that is a clear distinction of a rainfall and a drizzle. Also, if it is greater than 7.5 mm per hour, it is a heavy rainfall. So these values, if you could remember, it would be great. Like for if you are planning to see preparing for the competitive exams and all. And just remember, zero point 0.5 to 6 mm is rainfall, less than zero point 0.5 is nothing but drizzle. And the third option is sleet. So sleet is basically not a liquid form. This is basically a solid form, right? It is a solid form of precipitation. It is basically ice. Ice sheets we can call. It's a solid form. We can call it as ice sheets. And how they are formed is by freezing of raindrops falling through a layer of sub-freezing air. So the raindrops, as we can see the from the clouds after condensation, raindrops be falling, right? So there is a layer in the atmosphere. There is a layer in the atmosphere. It is having a very freezing, like sub-freezing temperature. So if it falls through this, these droplets will become gets converted into ice and it forms sheets, sheets of ice in the surface. So these, so in the ground surface, it will be like a sheet of ice. So this is very dangerous. Like if, like while driving or like walking over it, it will, this is very slippy, right? So, uh, so this is a dangerous form of precipitation. And so basically what we need to remember is it is nothing but a sheet of ice and it is will be laid over the ground surface like a sheet and it is cause formed due to when the raindrops process or falls through a sub-freezing layer in the atmosphere. Okay, so these are the points you need to note about what we say sleet. It is a very harmful because the ice coating because the entire ground surface will be coated by ice. Okay, so the answer is sleet, which is not a liquid form but a solid form of precipitation. So we can move on to the third question. So this question is related to the estimating the average rainfall. So if you remember, so if you have gone to the lectures, the precipitation first we saw how we can measure this precipitation, right? How this precipitation can be measured. And if you remember, we measure the precipitation. The ground data is measured using rain gauge, an instrument called rain gauges. So you have, so in the very first lecture, the very first week lecture, ma'am introduced you use some terminology called catchment or a watershed. So this is like when we are doing some analysis, we will be familiar, we will be doing that analysis in a particular area of focus, right? So if we take, for example, if we take a basin like a Ganga basin, if we can take an example of a basin, say Ganga basin. So if you see the approximate size of the basin looks in this way, and we have the Ganga river flowing through this and we have its tributaries, sub-tributaries like this. So this is this particular line, this is the boundary. This is nothing but a ridge. Ridge in the sense the elevation, this has the maximum elevation compared to this side and this side, right? So if we whatever water flows inside this, whatever rainfall this particular area receives, it will be flowing to this river. So that is how we define a catchment. So if it falls, rainfall falls outside this boundary, it will be flowing to some other river or some other basin, maybe some other basin adjacent to Ganga. So this particular boundary, that is the catchment boundary or the basin boundary, the sub-basin boundary, is the boundary of maximum elevation, and its neighboring elevations will be, we call it as a ridge. The neighboring elevations will be smaller than that. So whatever the rainfall happens in this particular area or the catchment will be flowing to this particular river. Okay, so such so we are now doing an analysis on this particular basin which I have drawn in this figure, and we know the rainfall. So we have installed different rain gauges at different locations here. So these red crosses are the locations of different rain gauges. So if we want to report what is the average rainfall for this particular catchment, so that we are doing this analysis for this particular catchment, right? So uh, if you want to uh, calculate what is the average rainfall in this particular catchment, so for that we will be using different estimating average estimation techniques. So we have the point data, we are converting it into a spatial average. So the different methods here are so we can go to the questions and then we can see different methods. So the question is, which method for estimating average rainfall incorporates the orographic effect? So the key points here are, we are trying to estimate the average rainfall and take a case that in this particular catchment there is orographic effect. Orographic effect, I think it is familiar to you, right? Orographic effect is nothing but if there is a mountain or a very hilly region in your basin, in this particular basin, say here it is a this side is a high elevation mountain region, or maybe in Ganga Basin, if you take the example of Ganga Basin, in the north side we have the Himalayas, right? So that is a orographic effect will be there. That is when the when the air masses travel, they hit this mountain and they raises up, and in the in that side where the air masses were coming, the rainfall happens there, and the other side will be deprived of rainfall. That is, if the mountains are here, so here in this side, this particular belt will receive very high rainfall, and this particular belt will be receiving very low rainfall. So in such cases, but then you can see there is a discrepancy, right? So here, if I take more rain gauges along this green line, then I will be getting a very high value for this basin. Right. And if I take more rain gauges, my more rain gauges falls in this particular red line, then I will be getting a very small rainfall, right? So there will be a discrepancy when we take the average or when we report the average. So in such orographic effect, in which of the that effect in which of these techniques are incorporated? That is a question. Okay, so before we can go through the options and then we can come to the answer. So before we go into the question, you have to keep this in mind. We have a catchment, and say there is a belt of a mountain in the up in the northern part of the catchment, and the rainfall in the windward side will be high, and the leeward side is small, and we have uh, ring gauges throughout the catchments, and there can be a case that we apply more ring gauges along the leeward side and less ring gauges in the windward side. So that discrepancy is also there in our catchment. So then we can see each of the thematic averaging techniques or the estimating average techniques, and which all will be having an issue, which all won't be having an issue. Okay. So the first option is arithmetic average method. So arithmetic average is simple. There is nothing that if we have like 10 or 15 or hundreds of range gauges, take the average of entire values. We are independent of where the rain gauge is falling. So all the rain gauges here, so these all are rain gauges. All the rain gauges we are taking the average and reporting. This is like in particular year, say in the year of 2024, this the annual rainfall is calculated for all the rain gauges. We take the arithmetic average and report that the Ganga basin has received this much annual rainfall in the year of 2025. So That is what arithmetic average method is. So if you take a case where I showed you in this particular red line, so this particular red line, so that is in the rain shadow region. There the rain will be less. So take an example, if I have more rain gauges here in this particular location, I put up more rain gauges in this particular location. So what happens is my average will be very less, right? My average is less because most of the rain gauges were falling in the rain shadow region. So this particular method is not suitable for that, right? So if it is not seeing where the rain gauge falls, so it is independent of that. So that's why this particular arithmetic average method will be reporting a very low value of rainfall if rain gauges are more in the shadow region. That won't be correct, right? So there this arithmetic average method fails. So if you could see the drawback of this method, so which we won't be applying to this our particular Ganga basin because we'll be getting a uh, it depends on the location of ring gauges, not on randomly we can place these ring gauges, right? So arithmetic average method is nothing but P bar. We will be calculating it as simple average 1 by n summation of I equal to 1 to n, and small n is capital N is the number of ring gauge pi. Okay, and this is so the important thing is this is suitable for physically and climatically homogeneous catchments. So physically and climatically homogeneous catchment. So this particular catchment, which we took the example of a Ganga basin, it's not a homogeneous catchment. It is like if we say physically also, physically the we have a physiography of mountains in the northern side and plains in the southern side. So physically it is not homogeneous. So we cannot apply arithmetic average method. Also climatically, if you see the in the Ganga basin which spans to the Rajasthan, that region, that is very arid region, like very dry region, very hot region. And also, if you see to the West Bengal side, it receives a lot of rainfall. So climatically, it is not homogeneous. So in such basins, so such areas, arithmetic average method won't be giving us a right estimate or right average rainfall. So whatever we are reporting will be wrong. So this is wrong. We cannot use this for orograph when we have the orographic effect. The second is the Thiessen polygon method. So Thiessen polygon method, uh, what it basically does is, uh, so we have taken example within this particular basin. I'm drawing a smaller area where we have a rain gauge here and a rain gauge far away here. So I am interested to know about a rainfall in this particular point. So what Thiessen polygon method says, the basic principle of Thiessen polygon method is that whatever whichever the rain gauge is closest to it. So this particular point we are interested to find, this particular point within our catchment we are interested to know the rainfall, right? So whatever the catchment or whatever the ring gauge value which is very closest to this point or nearest to this point, that will be having the that particular uh, ring gauge, whatever the rainfall is measured, that will be the value in this particular point. So if it comes to some a point or a point or an area close to this particular ring gauge, so this area will be taking the nearest ring gauge value, right? So if I could divide, if I could draw a straight line and divide it by perpendicular bisector, so this much area will be taken up will be under the we will assume that this much the first this just a minute this area will be on will take the value of this ring gauge 1 and the bottom area this particular area will be taken up takes a value of ring gauge 2. So this will be clear when we solve problems related to this. I have a numerical problem related to the ring gauge related to this and Polygon method. So this is the basic assumption. So there is a method how we can divide this particular area. And so the most important thing here is how to know which particular line divides this two area, right? This is the entire area of the catchment and how we can divide it with a line so that the this contribution will be this area will be having the ring 1 value and this particular area will be having the ring 2 value. So there is clear steps for this, clear defined steps for this. I'm not discussing it right now. We have a problem coming up in the numerical. So there will be in detail, I'll be discussing each of the step and we'll be solving the problem together. Okay, so only thing you have to understand here is what we are assuming here is that the nearest neighbor, we have a linkage values, whatever the nearest neighbor value is, that is for that particular location. Okay, so that is what is meant by Thiessen-Polygon method. And basically, once we know this area and this area, we can calculate like A1 and A2. So whatever, so the average P will be nothing but P1, that is precipitation in location 1 into A1 plus P2 by A2 by A1 plus A2. A1 plus A2 is nothing but is equal to total area, right? So if I can write this as P1 into A1 by A plus P2 into A1 by A. So basically we are taking the weighted average. So each of the precipitation we are giving weights. So here if you could see A1 area is more, right? In if you see this figure, A1 is greater than A2. Right. So A1 is greater than A2. So that means more weight will be given to the A2 precipitation value and lesser weight will be given to the P2 precipitation value because most of the area within this catchment lies close to the A1 or R1 range 1 and very less area falls close to the linkage 2. So that is the principle behind this. But here also the orographic effect it is not get taken into consider. It only takes into consider how much area the rain gauge within our catchment, how much what all how close the rain gauge are within our catchment boundaries. That is the only thing it takes into consideration. So it doesn't not if for example if there is a mountain here that it won't be taking into consideration that orographic effect that won't be taken into consideration. So it is a good thing that it gives more weightage to the rain gauges that spreads over a larger area in our catchment, larger influence of our catchment compared to the ones which are in the boundaries. Okay, so that is a good thing, but it still doesn't take into consideration of the orographic effect. So that is also wrong. Next, it comes the isohedral method. So before we go into the isohedral method, so this isohedral method also we will briefly discuss here and we have a problem. We have a problem in the numerical section. There we will be solving it in detail. So in isohedral method, what basically we are trying to just a minute. So what we are trying to do is, so we have a catchment. So in this catchment, isoheight. So isohedral method. First thing you have to understand is what is an isoheight. So isoheight is nothing but contours. So we know what is a contour map, right? Contour maps are lines joining points of same elevation. The same principle if the line instead of same elevation, same rainfall, if you could make a map, that is called the contour. That is called the what we say the isohyets. So if we could draw different, so these lines are lines of different contours. Okay, so each of this particular line will represent a one particular value of precipitation P1, P2, and P3. Okay, and we have areas within this A1, A2. So if we could make the contour map, there are different geospatial techniques which we can use to calculate these areas. Okay, so within here also there may be one another P4, P0, I am calling this. So these are and this is the area of our interest. So basically here our P bar is given by, so each area, if we take the area A1, okay, so uh, the area in the area A1, so in this particular area, okay, um, in this particular area which I've shaded A1, the rainfall is taken as the average of P0 plus P1 by 2. So this is the rainfall in the area A1 corresponding to A1. This we multiply with the area A1. Similarly, for A2, we are assuming that this area will have the rainfall P1 and P2, the effect of P1 and P2. So the average rainfall or average of that will be influenced by this particular area A2. So that will be P2, P1 plus P2 by 2 into A2. Similarly, you can write the other terms, right? So this is how we find the average rainfall using a isohedral method. So in this case, the advantage is that if there was a mountain here, if here it was a mountainous region in here in this particular location, so this P naught has the effect. The P naught will be, so if the air mass is flowing from this particular direction, the P naught will be the windward side, right? So that area will be receiving higher rainfall. So this higher rainfall will be taken into consideration by P naught, and P1 will be in the leeward side, right? Or in the rain shadow region. The P1 value will be smaller. So P naught will be very much higher than P1. And in this area of influence, we are taking the average of P naught and P1. So indirectly, we have brought in the effect of orographic effect, because these precipitation values we are using. So directly we are using those values. We have incorporated the orographic effect, right? So earlier what happened is we were placing rain gauges within this particular line. So anyway, the P1 is in a rain shadow region. It will be automatically smaller values we'll be getting, and we are taking the average and reporting that as Ganga Basin has already this much rainfall. That is something wrong, right? So here, if we have the ISO heights for different, so we have an ISO height for the ISO heights. If we make like a contour map, it has the entire extent will be covered, right? So it has the rain shadow region also within it. It has the high rainfall region also within it. So in a way, indirectly, it will be taken into account for the what is orographic effect. So in this particular case, instead of taking random rain gauges for this particular catchment, if you take the if we could take uh, different what we say ISO heights. So the different ISO heights and then take the average. So different ISO heights and like P1, P2, P3, and here in the rain shadow region also one will be getting P naught. This will be having the effect of ISO orographic effect, and we'll be getting a more accurate value. So out of this, so the third option, ISO heights, is the right option because isohydral method, indirectly it has the effect of orographic effect is being considered, which is not being considered in the option A and B. And the fourth one is a normal ratio method. So this is something not coming under estimating the average rainfall. This is, if you remember correctly, this is something we will be using to find the missing rainfall. Inconsistency in rainfall data, if it is there, if we have a station and some rainfall readings are not there, these inconsistency we will be solving, or we will be dealing with the help of uh, with the help of these methods like normal ratio method, arithmetic average method, such things we'll be using. Okay, so this is something we will be coming into, so it is not a part of the arithmetic average methods. So next, we'll move to the next question. Which of the following rain gauge produces a plot of rainfall values against elapsed time, that is mass curve, using a spring or weigh, weighing spring or weighing mechanism. So before we go to this question, I keep it in a pause. We can move to the fifth question. Yes, we can move to the fifth question, and then we can come to the fourth question, because here from this we will be familiar with what is a mass curve, and then we can come back to the rain gauge question. So a ISO height. So if we could read out this question. So this is nothing but is related to how we represent the rainfall. So we already calculated a rainfall. It can be for a rain gauge, it can be for an catchment. So we have the rainfall time series with us. How we represent this time series? Time series is nothing but something plotted in x-axis. We are plotting time, and it is changing with time. That is called a time series. Some quantity that is changing with time is called time series. And basically, what is an hyetograph? So ISO heights we already saw. So what we are saying, what ISO height represents graphically? That is a question. So anyone can answer this? Yes. Yeah. So we can quickly go through what all each of the terms are. The first one is the first option is cumulative rainfall depth by time. So that is means if I take time as hours, in hours. So for each hour, 1 hour, 2 hour, 3 hour, I'm measuring the rainfall, and each time I'm adding like one mm happened in first hour, 2 mm happened in the second hour. So in the second hour, I will reporting it as 3 mm. So it is accumulated we are taking. So that will be something rising, right? Always it will be increasing because each time we are adding values. So it will be something going in this way, in this way. It can be horizontal and it will go in this way. So this is cumulative rainfall depth, P in mm. So this is called a mass curve. That is cumulative. So this is, but first option is nothing but a mass curve, that is cumulative rainfall depth with time. So can anyone say what is happening here? This horizontal line. So this particular horizontal line, what it represents? This can also be a good question. If you're given with a mass curve, and mass curve from the term itself, it is clear, it is cumulative, so it will be always increasing, it won't decrease. So but it is parallel to the y-axis. What it represent? Hmm. uh, Mass is constant, we can say. Or if we are talking in terms of precipitation, the mass of precipitation, precipitated water, which we are measuring as depth. So the mass of water we are measuring as depth, right? So in this particular time, no rainfall has occurred, right? So if I can write P versus time, the first hour 2 mm happened, second hour 3 happened, third hour 5 happened, fourth hour no rainfall happened, fifth hour again 1 happened. So if I could uh, cumulative rainfall, if I could find first hour 2, then 5, 5 plus 5 10. then remains 10, then 11. So if you could see here, here in both the values 3 and 4, it is 10. Something similar to this particular thing, right? So what actually happened there was no rainfall happened. So when no rainfall happened, the cumulative mass curve will be a horizontal line parallel to the y-axis. So mass curve, as you said, it is a mass of the total accumulated mass of the rainfall, which is measured in depth. That is, we are plotting. And if the mass remains constant throughout that time, what this particular interval means, no more masses is being added to the system, right? So in this particular interval, if the mass remains constant, that means in this particular interval, no more masses of rainfall or no more volume of rainfall is or quantity of rainfall is getting added to the system. That's why the cumulative plot became horizontal. Okay, so this also can be a good question. So you remember that. So whenever this mass curve can be horizontal, and the reason is that the rainfall is no rainfall occurs in that particular period. The second option, so the first option is mass curve, it's not hydrograph, so it is wrong. The second option is rainfall intensity with time. So rainfall intensity already are familiar with. The first question, using the thunderstorm cell model, what we derived is nothing but intensity. Intensity is nothing but rate, that is time rate of rainfall. Like as you said, the mass that is coming in each time, instantaneous time, right? For that, we'll be plotting time in our x-axis and intensity will be denoting by small letter I, which can be like something like mm/hour, and we'll be using help of we'll be plotting. We are not using a line graph, we'll be using a basically a bar chart. So this is something a hydrograph looks like. So this is 0 hour, 1 hour, 2 hour, 3 hour, 4 hour. So what it represents is if this particular value is 5 and this particular value is 4, this is 3. What it represents is in the first 0 to 1 hour. That is in the first, if you see this plot, what is represented is in the first 1 hour, 5 mm per hour rainfall intensity rainfall happened. That is for the entire 1 hour, the rate was 5 mm per hour. That is for that particular 1 hour, 5 mm rainfall happened, right? And in the uh, second hour, that is from 1 to 2, the rate of rainfall was 4 mm per hour. That means if that rainfall had remained for 1 hour, then total depth of 4 mm would be generated. Okay, so this is something called a hydrograph. So you shouldn't get confused this. So this is the right answer. This is something called hydrograph. It's Y-E-T-O. This is something called hydrograph. You shouldn't get confused with this and histogram. So histogram is nothing but bar chart, right? So histogram is nothing but it is not a term that is been defined for rainfall alone. It is like a general term that even we can plot any data using histogram. So histograms are like similar to a bar chart. So the only difference is that we plot continuous data. Like here, continuous in the sense 0 to 1, 1 to 2, 2 to 3, 4. The y-axis is continuous. So you can, this is something called histogram. But in bar chart, the difference is like if we have what we say different uh, different rain gauges. If I plot in y-axis, I'm saying general example. If I could say the like different courses in NPTEL. So engineering hydrology is a course, and something like stochastic hydrology is one another course. Groundwater hydrology is another course. So these courses, how many are the total students registered? So this we can plot it using a bar chart. So this is the number of students. So here if you see the y-axis is discrete, it is not continuous. But in case of a histogram, the y-axis is continuous, 0 to 1, 1 to 2. Then we can see that bars are close to each other. There is no gap between, so there is a discrete gap between these bars, right? That we won't be making in case of histogram. That is the main difference between histogram and bar chart, and we can see people using these terms like for histogram they call it even as a bar chart, but histogram has a clear difference. It is used for continuous data for like rainfall. So here, when rainfall histogram is nothing but we are plotting rainfall in this particular rainfall depth in this particular y-axis. So basically, if the y-axis is rainfall intensity, that is mm per hour, then it will be hydrograph. And if the rainfall depth is in mm, that is depth we are plotting versus time, then it is called a rainfall histogram. That is a difference. So you shouldn't get confused with a hydrograph and histogram. That is two different things. So this is called a histogram. And there is something called discharge by time. Discharges means that is something you will come to learn in the coming lectures. Rainfall happens, it flows to the rivers, right? And in the rivers, it will the runoff will happen, right? The river will flow with the velocity or a flow rate. That is called discharge. Discharge versus time. So that is something called a hydrograph. So that is not yet covered. You just be familiar with this term. So this is nothing but a discharge versus time plot. Discharge means Q. Q versus time. Q is meter cube per hour, right? That is in the y-axis we will be having discharge Q, that is in the unit meter cube per hour, that is volume per hour, and in the y-axis we have time in hour, and it will be something like this. Unit hydrograph. Hydrographs that will be covered. So the correct answer is rainfall intensity versus time. That is called hydrograph. Okay, so we can come back to the last MCQ question. That is, which of the following rain gauge produce a plot of accumulated rainfall value against elapsed time? So this we already know. Accumulated rainfall by time is nothing but a mass curve. So that we already drew here. So, and we also know the case when the mask, what happens if a mask curve shows a horizontal segment, that means that at that particular segment there is no rainfall happening. And it uses a spring or a weighing mechanism. So here, if you could uh, if you could remember correctly from the lectures, we had discussed about rain gauges. So rain gauges are the instruments that are used to measure rainfall. So measurement of rainfall is done with the help of rain gauge. So basically there are two type of rain gauges. I briefly go through this. One is non-recording type. So from the name itself it is clear. And recording type. So non-recording type means we are not getting automatic measurements. So they are instruments, they are kept, they will be measuring rainfall in terms of depth by depth of water, depth of mass collected by a particular bucket or particular instrument, but they are not recording. We have to take and see or weigh and see or see the level and measure the rainfall that happened. That is called non-recording type. This was something that was used extensively in the earlier time. So that is you may be familiar with IMD, right? Indian Meteorological uh, Department. So they were using there are a lot of stations around covering the entire India, right? And these stations were made majority of non-recording type earlier. Now they have been replaced by recording type. The earlier the best example the example of the rain gauge they were using is the Siemens rain gauge. So Siemens rain gauge is a non-recording type rain gauge. So it basically has if you can see the more details in the lecture. So it basically rain gauge has a bucket. So in that, to water to go into that, we will be having a funnel placed over it, and it will be fixed in some location. So its base has to be fixed, and so base will be fixed with the help of a concrete block. So this is concrete block, and water will be stored in this, and we have to go and measure how much water is getting stored in this collecting bottle. We call it as collecting bottle. So this is a simple Simon ring gauge. So we can eliminate our first option because it's something that we have to go and measure. So it is not going to make any plot. It is not plotting anything, and there is no any spring or weighing mechanism. It is just a collecting bottle is there. There is a funnel, and water gets collected, and we have to go and measure whether how much is the rainfall happening. And the drawback is that if they are placed in some remote location or if the continuous rainfall happens, this will be filled, and it will be overflowing, right? So there is the chance it gets saturated. More rainfall cannot be measured in that. So we have to go and empty these collecting bottles, right? So these were the issues. And the next type is the recording type. So the recording type, they are of three. That is weighing bucket, tipping bucket. This weighing bucket is or like it is very much similar to weighing bucket. That is, these both are very similar. Floating, floating bucket, floating or natural siphon ringish. So I will briefly go through this. So in the weighing bucket rain gauge is nothing but, so there is a bucket. It's not a collecting bottle. We have a bucket inside that, and this bucket is being weighed by a weighing mechanism. So there is something here that is called a weighing mechanism. So under the bucket there is a weighing mechanism to weigh this particular how much ever water is coming to this. Okay, and this particular, so when more water comes to this, there will be a moment, right? There will be the weight will be different weights will be uh, different weights will be measured. So that weight which are being measured is connected to something called as a balance linkage mechanism, some mechanism which converts these weights, and it is attached to a pen, and there is a revolving drum over here, and so this is called a revolving drum. So basically what it happens is whenever the weight here, this weight changes, this balance mechanism will transfer these values, the change in weight values to the pen, and this there is a drum that is keep revolving around, which has a paper over it, and this revolving drum which is having a chart over it, and this uh, when the pen moves with the balancing mechanism, and the rainfall values will be automatically recorded in this particular drum. So it is calibrated in such a way that we'll be directly getting the plots of the accumulated rainfall. That is, if more and more rain, first ever this much rainfall happened, so that will be recorded in this particular drum. So maybe in this particular drum, if you could see the chart in this particular drum, So in this particular drum, if you could see the chart, so this is the chart that the pen is drawing. The first, it has this much weight. So initially, slowly it will be filling, right? So the weight has increased and that much mass has increased. And for some time, say for a 1 hour, no rainfall has occurred. Then for that 1 hour, this is access is time. Okay. Time means it is keep on revolving. Even if rainfall happens or not, it will the purpose is it keeps on revolving, right? So when it keeps on revolving, this will be keeping on rotating. So these good figures are there in the standard textbooks and also in the lecture notes. You can follow that. So I'm basically trying to explain the mechanism. So initially the weight increased and the pen was marking like this. And after some time, there is no rainfall happening, but the drum keeps on revolving. Then we can see that the pen is kept on marking this point. And then another rainfall happens, then the weight will increase, then it stops. So this is basically nothing but the cumulative rainfall versus time, right? So this is nothing but cumulative rainfall versus time, that is called a mass curve. So this is the mass curve which we have already seen here. So this particular drum with the help of the weight using that pen will be measuring. So as you said earlier, for that particular time, the mass will be constant, right? So the weight will be constant here because no more rainfall is getting added to that particular bucket. Okay, so in that we also can see. So basically this particular thing, that is the weighing bucket type ring gauge will giving us the mass curve directly. So finally I quickly discuss the tipping bucket. Tipping bucket is nothing but the figures you can see the lecture notes. So it basically has two buckets. So you can also search in Google. You can see the realistic pictures of these instruments. So we have two buckets, and what happens is the rainfall will fall into one particular bucket, and so this bucket is something somewhat I can show it in this way. It will be this plan view will be like this. Front view will be like this. Okay, so it has so So water will be flowing in this for some time, rainfall will be flowing this for some time, and when the rainfall depth becomes, this is important, 2.5 mm, there can be numericals based on this also. When the rainfall depth becomes 2.5 mm, this will tip, and this water of 2.5 mm gets collected in this particular container. And once this tips, and here the water gets collected, and when it becomes 2.5 mm, it will tip into in this particular container. So basically here there will be a pivot mechanism and this will be tipping. So each tip means the number of times it tips. If it tips 5 times means 5 into 2.5 mm has been collected in this particular container. So that is fine tipping bucket. It basically has a pair of bucket and it will be collecting water once 2.5 mm of rainfall is collected, it will tip. And the other gets filling, and once 2.5 mm is collected in the other bucket, it will again tip. Right. So you can make a plot of, with the help of this, we can get a plot of number of tips at what time each it is tipping. That is, if after 1 hour it tipped first, and in that 1 hour the total rainfall happened is 2.5, and after 5 hours it tipped again. Then the total rainfall in the next 5 hours is 2.5 mm. So in a way, it is directly giving us the intensity. That is, the first tip was in 1 hour. Second tip in 5 hours. The 1 hour first tip happened, and after 5 hours, second tip happened. That means the first hour, the intensity is 2.5 mm per 1 hour, and in the next 5 second tip happened in 5 hours. after 5 hours. That means from 1 to 5, that is 4 hours is there, right? So uh, second dip in the after 5 hours, so that means 0.25 mm was accumulated in 4 hours. So this will be intensity. So directly we can calculate the intensities. So basically there can be problems where they will be telling you the time in which the tipping occurs or the hours in which the tipping will occur in the tipping bucket, and you'll be asked to plot the heightograph. So will be asked to plot this particular heightograph. Heightograph is nothing but mm per time. So the first tip, if it happens after 1 hour, 0.25 by 1, that will be the intensity. And the second tip happens after 5 hours, that is 1 to 5, that is 4 hours are there. In 4 hours, 0.25 as filled, is 0.25 by 4. Similarly, you can find the intensities and plot the heightograph, right? So that is about these are the what we can say the MCQ questions. Now we can come to the so there can be better or like more MCQ questions related to the rain gauges and also related to the measurements of rainfall, presentation of rainfall, forms of rainfall. This chapter is something that repeated questions are being asked. These are like easy to score also. Repeated questions are being asked the previous competitive examination. And there is no compared to the uh, atmospheric water, that is the previous lectures where we are using complicated equations to calculate these what we say these atmospheric variables. Compared to that, these are very straightforward and easy. Okay, so now we can move on to the numerical type questions. So numerical, we'll be having a first question on the thunderstorm storm model. Then we'll be having one on the inconsistency and consistency of the rainfall data set. So we have a couple of simple questions from that. And finally, we'll be having a question on normal ratio method, which we also will be discussing. And the last two questions are very important. First one is the where we'll be dealing with Thiessen polygon method, where I'll be explaining you how this Thiessen polygon for simple geometry it is easy, but for difficult geometries it can be more complicated unless you know the basics behind this is clear. Then it will be easy for any complicated geometry. And finally, we'll be moving on to the isoheital method, where we have a cat spread and different isoheights are given, and we have to find the uh, using the isoheital method, need to find the uh, average rainfall. Okay, so directly we can start with the we have 40 minutes left, so we can start with the first question. The first question is determine the precipitation density. So directly we need to apply the equation for I. We have already derived the equation for intensity with the help of the thunderstorm cell model. So we have to find the intensity I from a thunderstorm cell with a diameter 5 kilometers. So as you explained, they are taking an area of 5 kilometer. Entire 5 kilometer area they're trying to model using the terrestrial cell model. The cloud base is at elevation. The cloud base is at 1200 meters. That is the base of our, that is the inlet of our, what could be, so inlet of our thunderstorm cell or the inflow region, and the average elevation is 10 kilometer. So 10 kilometer we have the outflow region. So inflow region height is 1200, outflow region is 10 kilometer. At the base, cloud base 12, that is at the cloud base, the parameters are given. So this is one step ahead, right? Usually we'll be given with the parameters at the ground surface, right? We'll be given with the parameters at the ground surface, and we can find the parameters at different locations. If we know the lab state and all, we can find at 1200 meter. We can also find at 10 kilometer elevations, right? So here instead they have mentioned us already given the parameters at the base of our what we can say the thunderstorm cell. Then we can find these parameters at 10 km elevation, and then we can proceed with the direct equation which we have derived and solve for the intensity, right? So at the base, that is 1200 meter, they have given the pressure is given, wind speed is given, and that air is both saturated at inflow and outflow. It is saturated air, so that condition is satisfied. And finally, the lapse rate is also given. Okay, so first of all, we can write what all are given. So diameter D is 5 kilometer, that is 5000 meter. Base elevation, that we call it as Z1, right? So two elevation is there. Base elevation is the inflow region elevation, and the outflow region elevation is Z1 2. Is Z2 we can call. Base elevation is 1200 meter. Z2 will be 1000 meter, 10,000 meter. That is equal to 10 kilometer. And velocity at inlet is velocity of air is 4 meter per second. That is also given. And temperature at the base. T1 is one is the inflow region and two is the outflow region. T1 is given as 25 degrees Celsius, and P1 is also given pressure at the base, that is 90 kilopascal, and lapse rate is given as 6.5 degrees Celsius per kilometer. And also we'll be making use of those constants. The constants are not given, but they should be known to you. The gas constant is for air is 287, and the density of water we know it is 1000, and G will be using it as 9.81 meter per second square kilogram per meter cube. Right. So these are the values we have. We can directly solve. So first thing we can do is we will start with the temperature always, right? We know the temperature at one particular elevation. How we can find it for the other elevation? We can directly use the lapse rate. So the temp T 1 is 25 degrees Celsius. That if we want to convert it into Kelvin plus 273.13, that will be equal to 298.15 Kelvin. And so that is the temperature. So we will be calculating the properties. So all properties we will be calculating at one location one we are calculating. So we already got T1, it is given. Now density of air. So density of air we solved a similar question previous time. So we'll be using of the gas law. So that is nothing but P1 by RAT1. So all values are given. P1 is 90 kilopascal, that is 90,000, divided by R is 287 into T1 is 298.15. That will be approximately 1.052 kilogram per meter cube. So we got the density at location 1. So the next is the uh, so what we are interested is to find the specific humidity, that is QV. We need QV at location 1 and location 2. So QV, if we want QV's equation is this relation, you remember, right? 0.622 ES by pi, that is vapor pressure by the atmospheric pressure. So we need to find vapor pressure, not ES, E by P. What is the vapor pressure? That is the next task. So we can make use of the assumption we are saying that all are saturated, right? If air is saturated, we can find there is an expression for saturated vapor pressure and temperature, right? There is also a plot for that. We already saw in the previous lecture. So that expression we can use. So ES1, the saturated vapor pressure one is 6.011 exponential of 17.27 into temperature. Temperature is nothing but 25. You have to substitute it in degrees Celsius in this particular equation. You have to be clear with that. In this particular is an empirical equation, so the unit matters. So should always put it in that particular unit. If you are using this particular equation, you have to substitute it in degrees Celsius. And here, since uh, RA is in Kelvin, we have to multiply per Kelvin. We have to multiply it in Kelvin. So that we have to be clear. Okay, 237.3 plus 25. So if you solve this, you will be getting it around 3169 kilopascal. So we got the vapor pressure. So we have the vapor pressure, we also have the pressure, so we can find the specific humidity at location 1, that is equal to 0.622 ES1 by P1, that is 0.622 into 3.169 kilopascal, and P1 is 90 kilopascal. Yes. This is in Celsius. So this is basically an empirical equations. So there are do you know what is a empirical equation means? There are equations like, for example, we can say F equal to ma, right? Force is equal to mass into acceleration. So the unit here, the it is consistent, right? The unit of force is Newton per meter square. That is kilo. So that will be no, unit of force is Newton. So that will be equal to, that is that unit, and the unit of the LHS and RHS are same, right? But these equations are called empirical equation. What do you mean by empirical equation is that the purpose is that we need, so how we derive a empirical equation is that we need the scientist, like the one who has derived this particular equation, the researcher who has derived this equation. So he wanted to calculate a relation between ES as a function of temperature. So he will measure the saturated vapor pressure for different temperature, like say 10,000, the 10,000 temperatures, different temperature values, he will measure ES, and he will try to fit to a perfect curve, and he will plot those values. So there will be lot of values. Here this will be temperature, that this will be ES, and he will plot a best fit, and he will find an equation for this particular curve. So this particular curve equation is given by this particular equation. Okay. So whatever the equation he derived, so that will depend upon what unit of temperature he used. While deriving this particular equation, he used the unit degree Celsius. That's why he got the constant 17.27 and 273.3 and all. If we had used Kelvin while deriving, there will be another value for these three constants. 0.6111 will be having some different value. Uh, 17.27 will be having some other constant value. So it all depends on what that particular researcher used to derive this particular relation. So this particular empirical equation is derived using degree Celsius as temperature. So we have to substitute it in degree Celsius, right? So every time when you are given with the empirical equation, always they will specify the units. So what is the unit of temperature that you have to substitute? Then what will be the unit of ES1 we will be getting, right? So these all will be mentioned along with the empirical equation. So this equation one is not valid in this way. We have to mention we will be getting ES in kilopascal if you put temperature in degree Celsius. Okay, so this statement will also come along with this equation. Okay, that's why we cannot put it in Kelvin. This is an empirical equation. So if you solve this, this will be QB1 will be around 0.0219. kilogram by kilogram. That's how we represent specific commodity. So at the location 1, at particular location 1, we got all the three values. That is, we got T1, rho 1, QV1. Now we can go to location 2. So similarly, you can apply this particular thing in location 2. So to start with location 2, we need the temperature, like, right, location 2. So first we need T2. So T2 we can find using the lapse rate. So lapse rate is nothing but as we go in higher altitude, how at what rate the temperature is decreasing. So that is given in the question as 6.5 degrees Celsius per kilometer. 1 kilometer higher altitude you go, the temperature will drop by 6.5 degrees Celsius. So using that, so how the altitude that we are going to travel is delta Z is the altitude we are traveling is from like 10 kilometer we will be reaching, but we are starting from the temperature we know is from the 1.2 meter, right? That is 1200 meter, 1.2 kilometer. So if you take the difference, it will be equal to 8.8 kilometer. So 8.8 kilometer is the distance that we are traveling from a non-temperature T1 to T2. So delta T if we know, then temperature at the second location is nothing but uh, 25, that is T1 25 raised to correct 6.5 into whatever the distance they have traveled. So that will be coming around uh, alpha is 6.5 degrees Celsius per kilometer. Mm. So 6.5 into 8.8, so it will be coming around minus 32.2 degrees Celsius. So it is not coming to a very realistic value, but it is still we can try to solve this question. T2 in Kelvin also we can calculate. So it just we have to multiply, add this with 70 plus 273.15. T2 in Kelvin will be equal to 240.95 Kelvin. Right. So we know the temperature now, and next is to find the pressure. So pressure P2, we have the equation P2 is equal to P1 into T2 by T1 raised to that constant term. The constant term is nothing but it depends upon it's a function of R, uh, gas constant G and alpha, right? So this particular n, if you calculate, it will be coming around. So as there is limited time, I'm going a bit quickly. That is, the power will be coming around 5.26, and we already know P2, P1 we already know that is 90, and T2 by T1 we know T1 and T2, that then the ratio will be 0.808. I'll be sharing you with this notes, and you can see. So just be with me when I explain. So it will be coming around the pressure at 10 kilometer is 29.3 kilopascal. So the pressure has dropped from 90 kilopascal to 29.3 kilopascal when we traveled a distance of almost 8.8 kilometer. Right. And we have the pressure, we have to just going quickly, we have to just uh, repeat the same thing. We have to find the vapor pressure. Vapor pressure, we will be finding the saturated vapor pressure. We have the equation 6.0011. It is in the empirical form 17.27 into minus 32.2 by, so it should be in degrees Celsius 37.3 minus 32.2. So if we substitute that, it will be coming around 0.040 kilopascal. So same thing, we are going to find all these values for location 2. And if we have that, we have QV2. QV2 will be 0.622 E by ES by P, everything for location 2. That will be 0.040 by 29.3 into 0.622. That is it. And it will be coming around 0.00085 kilogram per kilogram. So we got all the parameters we are given at one particular location. We were given with lab state. We got it for the other locations, right? So intensity. So this is direct substitution. We can substitute it as 4. The equation is for alpha A1 air density at location 1, V1 is certain velocity at this, location 1, Z1 is the inlet elevation, rho W density of water, D is the diameter, QV1 minus QV2 by 1 minus QV2. So in this particular equation, we know all the terms, we just have to substitute it. If we substitute that, it will be 4 into 1.052 into 4 into 1200 divided by uh, so this is the constant terms divided by 1000 into 5. This diameter is 5000, and inside the bracket humidity terms are 0.0219 minus 0.00085 divided by 1 minus 0.00085. So again, you can, if you substitute everything, we'll be getting this in all are in SI unit we are substituted. So we'll be getting in meter per second, right? So in meter per second, it will be around 8.51 into 10 power minus 5 meter per second. So this is the answer. And if you want it to report in centimeter per hour or some other unit per hour, if you want to report, so this is a meter per second. So to convert it into centimeter, I'm reporting it as centimeter per hour to get a more realistic value. So I'm multiplying it with 100 so that it gets converted into centimeter. And per second is this much. So per hour means in 1 hour, 1 second, if this much happens, in 1 hour, more quantity will happen, right? So we have to multiply it with 60 into 60. That, that is 60 seconds into 60 minutes. That will be 1 hour. So that will be something equal to 30.64 centimeter per hour. So this is the rate at which the ground rainfall will be falling to the ground if we have a atmospheric column which is having these values at an elevation of 1200 meter, given that the cloud the outflow outflow of the warm air occurs at an elevation of 10 kilometer from the surface. Okay, this is how we apply this particular equation. So the only thing you have to keep in mind is this particular pattern, how we in which we solve it. So we will be always given with the atmospheric parameter at one particular location. So you should be knowing how to find it for some other elevation. So that is clear because we have the lab state, we have the gas constant equation, we have the pressure equations, everything we will be having. And if there is the condition that is saturated, we can also use this empirical equation and we can come up with these all these parameter value at different elevations. Once we have the these parameter value at the inflow and the outflow elevation, then we can directly apply this particular equation and this substitution. The main part is finding these parameters, that is air density, specific humidity at the location 1 and location 2, that is the inlet and the outlet. Okay. So there are a couple. Next two questions are simple questions. It shouldn't take much time. The first question is, a catchment area has six existing rain gauges. So it has six rain gauges. The annual rainfall recorded at these stations are so each rainfall, what is the rainfall that is being recorded that is given? There are total six. If the permissible error, so there is an error to estimate the rainfall mean. So if we when we take the rainfall mean, if the error is allowed is 8%, calculate the optimum number of rain gauges required for this catchment. So that is we in this particular catchment we have only six rain gauge. Okay, they are working with a six ring gauge and these are the values. And if the error allowed is only 8%, whether the whether we need more ring gauge or not. So this is based on how much is the variability in these values. If the variability is very large, that means that in that particular catchment, there are the rainfall variability is very large, right? So there we need more rain gauge. If the variability is less, that is all values, if these values, if we observe, if they are lying very close to each other, then there is no need, that is uniform rainfall is happening. There is no need of more rain gauges. Six will be enough. So here also if you could see the values are almost lying between 850 to 1100. So these are like changing with like almost maximum range is about 250 or 300 mm, right? So that is all values are lying very close. So seeing the values we can say they are homogeneous and the six should be enough. We don't need to go for higher. So but that we can see how we are going to solve this. But if you take a case where if one particular ring gauge was reporting something like 250 mm and other was reporting something like 2000 mm, so that drastic changes is there, then the catchment is having that catchment has very heterogeneous rainfall, right? In such cases, we will be requiring more rainfall to account for the variability. So that is the principle that we are going to use here. So basically what we need to find here is first thing we need to find the mean rainfall that is P bar. So mean rainfall is nothing but the arithmetic mean that is just the summation of this that is 850 plus 1100 plus 950 plus 1200 plus 900 plus 1050 this divided by 6. So that is 6050 by 6, it will come around 1008.33 mm. So this is the rainfall happening. And next thing is we need to find the standard deviation. What is the variability? This is the mean value. And next is standard deviation. Standard deviation is clear. I hope you all be knowing. These are statistical terms, mathematical terms, right? So standard deviation sigma n minus 1, that is 1 by formula is 1 by n minus 1 square root of xi minus x bar the whole square by xi minus x bar. Just a minute. So instead of x, I will use directly precipitation, that is P, that is square root of some xi minus P by whole square by n minus 1. So this is the formula for finding the standard deviation uh, of a time series or any series. So this is nothing but we have to take the summation of that is 850 minus mean 1008.33 the whole square plus the second value that is 1100 minus the mean 1033 the whole square plus 950 minus 1008.33 the whole square. Similarly, next is 1200 minus 1083.33 the whole square plus 900 minus 1083.33 the whole square plus 1050 minus 1003.83 the whole square. So this is the numerator term divided by n minus 1. So the total n is 6. 6 minus 1 is 5. Right, and the square root of this. If we do this, we will be getting the uh, standard deviation sigma n minus 1. We'll be getting it as 131.97 mm. So we have the mean and standard deviation. So next thing we need to do is to find there is a term called coefficient of variation, CV. I hope that you are clear with this in the lectures. CV is nothing but it shows how much the percentage of variability, how much it is varying compared to mean, how much it is changing. So that is nothing but the how much is varying. The variability is given by standard deviation. We can see each value how much is changing from the mean. Each value how much is changing from the mean. That only we took the average, right? Took the square so that the positive negative values cannot get nullified. Otherwise, this positive and this negative value get nullified, right? The total variability we won't be getting. Then sigma n minus 1 by mean we already found out p bar. So this particular percentage is called uh, this particular percentage, that is p bar into 100. This particular this report as a percentage is called the coefficient of variation. How much is the spread? So if you substitute those values that we calculated, that will be 139.7 by 1008.33. That will be coming around 13.09 percentage. Right. And for optimal, so if we have so this is the actual error, right? Coefficient of variation is the actual error in the variation, or actual spread of the or historical variability of the range gauges as of now. And we have given that the permissible error is 8%, right? So there is an equation that is for to find the optimum number, that is coefficient of variation, whatever is the variation is there, divided by error, the whole square. So this is the equation. You can make a note of this. Such questions are also very usual in while we are dealing with precipitation data sets. So this is the equation. You can make a note of it. And in optimal will be given by 13.09. So make sure that you substitute both in percentage or both in decimals. Divided by 8. Here both are in percentage, the whole square. So that will be coming around 13.09 percentage. No, sorry, it will be coming around 2.68. So we should always round it to the next number because these are numbers of ring gauges. So that we have to always round off to the next whole number. So we will round off it to 3. So it says this particular catchment requires only 3 rain gauges. If the permissible error is 8, only 3 rain gauges was enough. But we have already provided 6 rain gauges in the question. So the question they are asking is how much more rain gauges are required. There is no need of additional rain gauges. It is more than sufficient. The optimal number of rain gauges is given by this particular equation, and we are getting it as so optimal number of rain gauge is given an optimal, that is equal to CV by error, coefficient of variation by error, the whole square. So number of rain gauges, number of additional rain gauges required equal to 0. Okay. So we can move on to the next question. So this is a simple question. It's a direct substitution only. So the question is, a catchment has five existing drain gauges with coefficient of variation 30%. So the CV of the catchment that we just calculated in the previous question that is directly given 30%. And N is also given that is equal to 5. Which of the it is desired to have a coefficient of variation. So CV desired is how much it is? 10%. So what is the total number of drain gauge required? So the equation is this ma'am is taking the class N desired is equal to CV existing, whatever the CV is there, CV desired the whole square into N existing. So that will be 30 by 10. Yes, 30 by 10 into 5. So that will be number required will be 3 square into 5. So that will be 45. 45, yeah. 45 is the answer. So we need 45 ring gauges are required. Total number of ring gauges required here is 45. Right, we already have 5. So we need how much more? 40 more are required. Okay, so this is another way to calculate the optimal number of ring gauges. So two ways are there. In a way, they both are connected. So we have like this is also direct substitution question. So this is estimate the missing rainfall using normal ratio method. So here we are using normal ratio method. And normal ratio, for that you have to understand two things. One is the what do you mean by normal rainfall? Normal rainfall is that a particular, if you say there's a particular station for the previous 30 long period, like for a 30 years, how many rainfall, how much rainfall has occurred. So that value, mean value will be there, right? So that is called the like usually where will be taking it as 30 years. So that rainfall is called the normal rainfall. So that value we can make use even if those if some particular year the rainfall is missing, we can make use of the 30-year data which we have already having. With the help of that, we can find the missing rainfall of that particular station. That is the meaning of normal ratio method. So basically, what it does is what it's saying is if you take any station Px and it has a ratio with normal ratio Px by Nx. Right. So this particular ratio can be calculated. This ratio is nothing but the arithmetic average of, if we say in this particular case, there are three stations, right? So this particular ratio of a missing station, in this particular case, so there are total of four stations. The NX station, the rainfall is PX is missing. So this is nothing but it is the average of these ratios. So average of this ratio means P1 by N1, P2 by N2 plus P3 by N3. So average means these ratios by 3. So this is what you meant by normal ratio method. So they are saying the ratio of precipitation by the normal value at one any location is equal to the arithmetic average of those ratios. So these we know these ratios for three locations. If you take the average, that will be equal to the missing location value. So we can apply this directly. So we need to find Px. So P1 is 750 by N1 is 700. P 820 by 800 and 900 by 850 divided by 3. So nx we have to move to the other side. So nx is already given the question, that is 800 into 800. So you can solve this. You will be getting around 841.3. 36 mm. So the missing rainfall we have found out using this. So only you don't have to by heart this equation. Just remember the P by N ratio for any unknown station will be equal to the arithmetic average of the P by N ratios. The P1 by N1 plus P1 by N2 plus P1 by N3, that is the average means divided by 3. If there are 10 stations, then the arithmetic average of those 10 stations. So this particular side, the RHS is arithmetic. In this way, if you remember, you won't be forgetting this equation. Average of the P by N ratios. Okay. And RHS, LHS is the P by N of the missing station. Just remember in this way, you won't be forgetting this equation. So we can quickly move on to the decent polygon question. So a rainfall event occurred over a catchment is recorded using three rain gauges. So there are three rain gauges A, B, C located at the vertices of a square catchment of 50 by 50 kilometer square. So we have a square catchment. So first thing to do is to draw the decent polygon. So we have a square catchment. Okay. So it is, I'm naming it as say ABCD. A, sorry, B, C, and D. Okay, so they are saying rain gauges are there along the vertex A, B, and C. So here a rain gauge is there, here one rain gauge is there, here one rain gauge is here. And this square that is 50 kilometer by 50 kilometer, that is our catchment, which we are focusing on. And there is rain gauge in these three stations only, three vertices only. There is no rain gauge in the vertex D. Okay, so now, and they have mentioned the rainfall at PA, PB, and PC. That is, the rain gauge at A measures a rainfall of 95, rain gauge at B measures a rainfall of 75, and rain gauge at C measures a rainfall of 40. Right. So these values are also given. They are asking us to find the average rainfall for this catchment of this square catchment. We need to find. Okay. So so the first step. So the very first step is what you need to do is to join all the join all the rain gauges. We have three rain gauges. We have to join these rain gauges using straight lines. So that is the first step we have to do. So if you join that, so these lines of A, B, and BC is already joined, right? So only thing we have to join is C and D. So AB is joined. So basically we need to join each of the rain gauges with straight lines. So AB and BC is already AB and BC we have already joined. So only thing is we have to join AC. So once we join the rain gauges, the next step, join the rain gauges using straight line. The next step is to mark the perpendicular bisectors of these lines which we just drew. So we just drew these lines and we are going to mark the perpendicular bisectors. So this is the perpendicular bisector. Perpendicular bisector means should be the midpoint and should be a 90-degree, right? So this is the perpendicular bisector and this is the perpendicular bisector. So these are the bisectors and perpendicular bisector will be making like this. This is the angle 90-degree it will make it and it will be crossing here and here. So this will be also 90 and with along this line also I have to draw the perpendicular bisector. So this should be making 90. 90 degree should be with the perpendicular bisector of the line joining the uh, ring gauges. So AB I drew, BC also I drew. Now for AC I have to draw the perpendicular bisector. So that will be moving like this, right? So based on this, we can segment the areas. So if you could see, the area will be enclosed. Now the area of each of the ring gauge will be enclosed by this perpendicular bisector which we drew and the boundary of the catchment. So this particular area, the yellow area is for ring gauge A1. This blue area is for the ring gauge. So these are the area enclosed by the perpendicular bisectors and the boundaries, right? So this will be the area for ring gauge B. And this particular area, the remaining area, this particular area will be the area where we'll be receiving the rainfall PC. So this is how we draw these some polygons and find the areas of influence for each of the precipitation. Next is just to apply a weighted average technique, right? So in this first we have to find three areas. So the areas are, so this is A, B, this is A, and this is AC. Okay, so AB is simple. So AB is nothing but 25 into 25. Yeah, 625. And AB will be equal to AC, right? AB and AC are similar area. That how we can find. So that we can divide it into a triangle, this particular triangle and this particular triangle, right? Or we can do it like a rectangle and a triangle. So this particular rectangle, 25 by 25 rectangle, and this particular triangle will be giving us the area, right? So we just have to find 25 into 25. That will be is the area of this particular rectangle followed by this particular triangle. This particular triangle is half into base into height. So this is 25. This is also 25, right? So that will be area of a triangle is half into base into height. If we do this, we'll be getting this as 937.5 kilometers square. That is the area of AB and AC. So if you take the sum, 625 plus 2 into this thing, we'll be getting the total area. And so the P average will be nothing but the precipitation at A is 95 into area of A, this is area of, mm, so this is 95 into area of A is nothing but 937.5, right? So this is AB, sorry, made a mistake. AB, this is AA and AC, right? Yes. Plus uh, our second area is AB, B is 75. 75 into the area there is 25, 625 plus 40 into is 937.5 divided by the total area. Total area is nothing but 50 into 50, right? So the final answer, it will be coming around, so we can calculate it, this will be coming around 66.875 mm. Okay, so the main thing is how we can find draw the decent polygons and how we can delineate these three areas A, B, A, C, and AA. Okay, so finally we can, this is the last question, this is a simple question. So we have given with the isoheights, we have to just find the aerial rainfall using the isoheightal method. So for this, I already told you, whatever be the average, the area between these two isoheights, whatever the area is there, that will be having the average of these two isoheight values. So 1 and 2, so 1 plus 2 by 2, this average value will be for the 30 kilometer area. So basically, the equation we can write, and also if you could see, there is a contour, closed contour here. So that is something you can note. There's a closed contour here. So within this closed contour, that area is 20, and the rainfall enclosing that is 10 centimeters. So there we don't need to take the average. So entire this area, inside this area, the rainfall is 10 centimeters. We are getting a closed contour. So there we can take directly 10. So what we'll be doing is, I'm calling from this side as A1, and this as A7, A6, and these are rainfall of R1, R2, R3, R4, R5, R6, right? So using this I can write. So the average rainfall will be first this particular area, that is 10 centimeter into 20. There we don't have to take any, this is an enclosed contour. So whatever the rainfall is enclosing that, we can take directly the value. Okay. The one thing is done. The next thing is 80. 80 kilometer square is the area. So this is 80 into, so what is the average there? That is 10 plus 8 by 2, right? 10 plus 8 by 2. So this area is done. Let's move on to the next area. Next area is 200. So 200 into, what is the precipitation average there? So it is enclosed by 6 and 8. 6 plus 8 by 2 average rainfall. And that is done. So the next is 1060 kilometers or so. 1060 into 5 plus 6 by 2. So these are the enclosing area. And next is 110. 110 into the enclosing ones are 2 and 5. 2 plus 5 by 2. And and finally, the last one is 30. So 30 into 1 and 2. 1 plus 2 by 2. So this all divided by the total area. So total area will be sum of all the areas. 20 plus 80 plus 200 plus 160 plus 110 plus 30. Right. So this is nothing but A1 AIRI summation divided by summation of AI. Nothing. So it is easier to write without writing the equation. We can directly see in the plot. We can write this. Just write the precipitation multiplied by the area. Again, the area multiplied by the average precipitation. So you can solve this. You can check the answer. Maybe there may be some calculation mistakes. If there is any calculation mistake, I'll be correcting it and I'll be uploading it in the while uploading, I'll be making the correction and doing this. So you can try this. All it will be giving around 5.825 mm. Right. So only point you have to note here is that when we have a closed contour, you can take the area closed contour. Then we don't have to take the average, where that is that the entire area is enclosed by 110 centimeter rainfall. Okay. So that is for today's class. So we can stop here. So if you have any doubt in any of these questions or any other assignment questions or anything, if you have any doubt, you can contact me. My email ID is gmail.com. My name is J. So if you have any doubt, you can contact me through this email. So I'm stopping this section. Thank you for joining. हाँ AKHIL JNANADEVAN. Okay, thank you. Thank you. Which one? No, 5 we came back and solved it, right? 5 we solved it. Yeah, yeah, we have done. Yeah, yeah. Okay. Thank you.